Hello, my name is Tianyu Ma from Cornell University. I will present my paper Hyper-convolution networks for biomedical image segmentation. For many computer vision applications, especially in biomedical domain, long-range dependencies are important. And to capture that, we need large receptive field in CNNs. We can use expanded convolutional kernels, but they'll significantly increase the total number of learnable parameters, which might lead to overfitting. There are other works that increase the field of view without additional parameters, such as dilated convolution. However, they also have their own limitations. For example, dilated convolution uses sparse kernel, which can be less effective for tasks such as image segmentation, which requires pixel-level predictions. What we really want is to have dense convolutional kernels with large receptive field without additional parameters. We propose hyper-convolution, which uses a small neural network to generate kernel weights. For kernels with arbitrary size, regular convolutions learns every kernel weights independently. For a 5x5 kernel, it would require 25 parameters. Hyper-convolution, however, learns a function mapping from kernel coordinates to the kernel weights. For example, to learn a 5x5 kernel, the input of the hypernetwork will be the xy coordinates of the kernels from -2 to 2. After several 1x1 convolution, the output will be the convolutional kernel. All the learnable parameters are embedded in those 1x1 convolutions, and more specifically, the number of channels of these convolutions. In other words, hyperconvolution decouples the size of convolutional kernels with the total number of learnable parameters. So we can have convolutions with large receptive field, but even less parameters. We test our method on both liver lesion and brain lesion segmentation tasks. The liver lesion dataset contains 131 images, and brain lesion dataset contains 21 images for training, and another held out 61 images for testing. All images are 3D, but we use 2D slices for training and testing. This figure shows the die score for both regular convolution and hyperconvolution models with different labels indicating different numbers of channels used in the architecture. As we can see, across a wide range of models with different number of parameters, simply replacing convolutions with hyperconvolution, we obtain a consistent performance boost in terms of die score. Another feature of hyperconvolutions is that the kernels are naturally regularized and smooth. Here we show random convolutional kernels of an unit baseline and its hyperconvolutional counterparts. The high-capacity model has the same number of parameters with the unit baseline. Those numbers on the left of each panel are second-order Laplacian of the kernels, lower number indicating more smoothness. As we can see, regardless of the model size, hyperconvolution always learns much more smooth kernels compared to the baseline. We experimentally demonstrate that the hyperconvolution models can be trained to mimic the kernel of the unit baseline. Therefore, the smoothness is not the result of limited capacity of hyperconvolution models, but due to its unique learning dynamics. You can read more about it in our paper. One of the benefits of having smooth kernels is that the model will be more robust against noises. This is especially important for medical imaging applications because during acquisition, medical images such as MRI might contain different levels of noises. In this experiment, we first trained the segmentation model on clean images and test on images with different levels of noises. We can see that die score of regular unit quickly decreases as we add more noise to the image, but the drop for hyperunit is much more slower. In conclusion, hyperconvolution enables neural network with expanded receptive field without increasing the number of parameters. It offers superior performance on biomedical image segmentation tasks and is more robust against noises during testing. Thank you very much.